Okay, so for today, I would like to talk about, ultimately we'll talk about the multivariate normal, of course, but I do want to spend the first 10, 15 minutes talk about the question that I posted on Moodle. And I saw some of you reply to it already, which is good, and I hope most of you got the chance to think about it, is where you're gonna have the extra layer of hierarchy. Not layer of hierarchy, more like if I now want to have different variants to be different as well. Like so far with the school exercise, like the school data math score, I guess. So with the math score, we have done, so the hierarchy that we have done before is y1, y2, to all of the yj. And we have each of the school have a school specific mean. So this is the hierarchical model that we have done so far. So for that, we have a normal mu tau square, I guess, over there, to assume that each of the school specific mean gonna follow the same normal distribution. Okay? And down here, because for each observation, we have, so what, let me do this. So that yij given mu j follows a normal mu j and sigma square. So that was the simplified model that we talked about. You only have one sigma square for all different for all different observations. So over here we have one sigma square. Okay? So this is saying that no matter what group, like what school you're in, and no matter which student you are, you're gonna have the same variance varied around the school specific mean. Okay, so this, like last time we said it's restricted because, I mean, you have fewer parameters to estimate, which is the good, but it might be too restricted, your variance will be the same for the normal model. So one thing you can do is to have this to be school specific as well. Okay, so that was the Moodle post. So I hope you got the chance to think about it. So two things. One is how to expand or change this particular representation here to accommodate this. This is one problem. The other one is how you can incorporate extra signal. If you have your laptop with you, I think some of you already replied to that question, which I think is correct. But if you have your laptop with you, so you can just change to accommodate this extra sigma j square. And since Jack's really fast, you might be able just to try it really quick before we move. Okay, so I will post it, yeah. So break into small groups, talk about it, and I will bring the code on my laptop and I share my screen. Two things, okay? The huge, okay, now I see it.
Oh wait, I can scroll.
Yeah, you probably have to download it, yeah. But Eli's is also a photo, right?
Yeah.
Yeah, so this is, I mean, if you go to Moodle, it's under hierarchical modeling, and then it's in the discussion board. It's the graphical representation and Jack's code to implement modeling HOF 8.5. So yeah, some of you already posted code as well as graphical representations over there, great, but I wish every one of you should think about how to do it. Also implement the code really quick. Oh, yeah. Yeah, I saw it happen, but only in this region. Yeah, the seats should.
For example,
Yeah, so that's okay. Let me bring up my laptop first. Yeah, it's Jack called Jack's hierarchical model for math score is JAX. So that's the original JAX code. I corrected the typo Becky pointed out, so I think it rounds just fine, reproduce the same results. But now what I'm asking is how you can adjust the code to include the different okay? This sigma J is different variance parameters for different school. I think some of your Moodle posted already, but I would like you to think through and then try it with your laptop really quick. But I didn't notice that, I guess Becky just now posted saying that she couldn't get the same result. We might all have to go back into it and discuss it Wednesday, but I do want to talk about how to just to enhance the understanding of text. Okay, I will talk about the graph representation first, and then can go back to do the code. But okay, so here I think both Eli and Serenity did a good post about, oh, sorry, it's just big, but I can show it. Okay, so I think the way that Serenity did is very similar to what the textbook does, so just bear with us a little bit. So it's a little bit big, but over here you see like Y1, Y2 until Y99 or Y100, they are just in the middle. And on the top, we're just doing, oh, I should just download it, right? Can I? Export, sorry. How can I? Sorry, give me a second. Sorry about that. Give me a second. I think it's because of the sharing. Let me turn. Okay. Stop share. And then, yes, I got it here. Okay. All right. Right. So this is the representation. So on the top is what we had before. Okay. So in the the Y's are observations in each school, and then you have a school specific mean, each mu j, and then each mu j is from a normal distribution center at mu and variance of tau square. And down here, because you're having a uniform, I guess yeah, you can think of it as a shared sigma square for each of the normals. So you have a 1 sigma square over here. But down here, to expand this model into one more hierarchy, you can think of it as one more, but also just like the same hierarchy as well, because that's at the school model. So on the top, everything is the same. But down here, the sigma will be school specific. So you have 100 sigmas over there. And down here, I guess the notation Serena is using is theta and tau 0 square. I guess might be a little bit off, but because over here, sigma should be inverse gammas. Okay, but the representation itself is right. You just have one more expanded to a lower level, and you're just gonna have all of the sigma j square being drawn from an inverse gamma. But over here, I guess we should use a inverse gamma to represent it, which is more in line with what we have done before. So this will be the way, if you follow the book, you will be able to do that. But I also want to share what Eli did on, give me a second. Yeah. So there's another way you can express this. So I think what Eli did is following what Professor DeLeo had done, using all of the parameter, like you show all the distributions over there. So this is the same idea. So you see that in the middle is all of the datas, all of the Y's, right? And then each of them gonna have a school specific mean. So here Eli is using theta, but it's the mean, it's the mu that we have seen before. So it's gonna be the same normal distribution over there. But you expand it further, like towards the lower bottom over here. So this again is each of the sigma square. And then here it's using the inverse gamma, I think. So it's V null, nu null, and sigma null square. And then all of the blue distribution, like the things in blue over here, is trying to show you it's actually going to follow a particular distribution. Okay, so both of this work. And I guess, did you get this on iPad? Yeah, I guess now, like even now using all of the zoom function, I realize because of the color coding that I can do when I write, this becomes, I guess, more efficient and straightforward as well. So both of this will be a representation of the expanded model. Okay? And okay, so 5 more minutes to talk about the code itself. So if you talk to your neighbors about it, and if you can demonstrate it using R, that will be good. So if you open the book 8.5 talks about the results. If you have expand the model to include sigma j squared, so that will be a benchmark that you can compare to. But you need to figure out the correct way to do the JAX coding. So it's on page 143. Okay, that will be the results for the next few pages. You can bring a laptop, try to talk to someone, sit with someone who has a laptop. The JAX code, to treat it, I don't think it's that hard. So we're going to look at that together. And the specific justification, we might have to go back and talk about it on Wednesday at the beginning. But for now, I hope each of you got the chance to do the JAX code a little bit, and then we're going to change things together. So JAX is, yeah, they derive everything for you. And to be honest, I think they actually had multiple different sampling schemes behind the scene, and they automatically choose the one that's most efficient. So there is no way, because I was looking online as well, I think some people want to use a specific sampling method for their Gibbs sampler, but unfortunately you cannot choose it. So Gibbs as a package itself does that for you. Yeah, but to answer the other question, yeah, they do the derivations themselves with it. So think of it being very smart and doing all of this for you. But for the normal case that we have been working on, even if you look at 8.5, like the textbook, once you have the one more varying sigma square, you can still derive it because you still have, I mean, 8.5 tells you how to derive it, but and then they run the code over there and show all of the results. But right now the task is first how to implement in JAX to add that layer of the changing sigma j square. And second, can you replicate the result? So yeah.
Distribution is through sampling. The full conditional view is the priorities.
Oh, I see.
So I just like this is something first of all. Like I don't really think this is it's not normalized. This doesn't know a lot of very instructive something like that. And it doesn't explain very well why it just moves on. Right, so the other parameters are pretty good. It's just this, it's new conditional.
And that might be the case that if you're doing rejects, they don't give you the same results. I don't know yet.
Yeah.
Yeah, but
oh yeah, so that's one of the things that's nice.
So I guess one thing, right? So one thing you can do is if you don't know, so over there, can you put a fire? Sigma zeros, or no, just a number.
So for news,
Yeah.
I assume it could fire.
Okay.
But they say there's no common fire.
Right. And then they derive.
And then they derive it with it based on the geometric.
Okay.
So it's computer.
Yeah, or I mean, inject, you can just put a number, right?
Yeah.
So that's what a scalar for that number to
Okay.
represent. So maybe for now, let's do that, because again, it might be a little more correct than exactly what they did in the book. Yeah. Right. So Eli was saying, if you read the book carefully, you look at page 144. They have a part about, so because you try to get a different sigma j square for each of the school variants, so you put an inverse gamma nu 0 and sigma 0 square, but you're gonna have to, so they derive on page 144 as how you can come up with full conditional distribution of the two hyperparameters. So it's a little bit involved over there. And it looks like, so what I was trying to say is once we move the code in JAX or trying to implement it through JAX, we might not get exactly the same number just because the way that they are doing it might not be directly transferable into a JAX code. So I'm just saying that like the one that we're gonna look at together was mostly about how you can change the code into adding this one extra sigma square, like sigma j square to be changing across different schools. And then in terms of replicating the results, it might be more involved than what we thought, but for now, we will, I guess, keep trying over here. Okay, so here, this is the code that we had before. Okay, this is only mu j is changing, so this is the part that you see over here. It's school specific, but the variance sigma square is fixed. Okay, so a couple of things, I guess, like you have to change something over here because now you have to make it to be school specific, and you probably need one more loop down here, or like just in the same loop as well, going through different inverse sigma j square. Okay, so I would just start like, I guess, coding a little bit. That will just be one way you can do it, but you might have different ways of doing this. So if I, again, let it to be school specific, so I just have a underscore and J to represent that to be a vector, and I want a school specific J, right? School specific variance. So I'm gonna have this inverse sigma square underscore J, and then down here I have bracket. In the brackets now I'm treating this to be a vector, right? So I want that specific piece for school J. So I'm gonna have school over here, bracket I tells me what is the school itself. Okay, so this is the first change that I think you need to do. The second change is over here. Is I just write it in the same loop because both of them are looping through J. Okay, so what you're gonna do, I guess you can do inverse sigma 2 J, and it's about the J itself. So what do we put? We put anyone from the textbook, what they're doing? So down here, I wrote in the original case, this is the inverse gamma, right? Okay, so I guess over here, so down here, this is all the priors, right? Down here, this is all what prior was written, but now because we have this one more, let me zoom this in, sorry about this. Yeah, this is easier to see. So these are all the priors that I put, but now, and this back then, inverse sigma squared, just part of the prior over there. But now I should have the D gamma over here. And what will be the numbers? Or like the parameters? So the textbook was using nu 0 and sigma 0 square. So if we just keep using the same one, I guess you will do divided by 2, and then nu 0 times S20 over 2. So if you do that, this line should go away, right? Because you don't need to specify the prior. But don't forget, you need to do something about the nu 0 and S20 over here, okay? So if you keep doing what we did before, this will be the priors. I guess that will be one way you can do it. But the textbook seems to be doing it in a different way. So I haven't run it myself yet because I want to just like do it real time with everybody else in class. But I think this will be my first try to update the code in order to accommodate that one extra layer. Yeah, Katie.
I don't understand why are you going to put a new distribution on 0 and S20?
Right, so, okay, the way here I'm doing it is without a new distribution. But the textbook, I think, does talk about new distribution, like, I mean, a prior for both of them. It's just unclear to me at the moment as how they're putting it. So I think, like, say over here, say they do put a conjugate class of prior for sigma 0 squared to be the gamma density. So they put a gamma AB over there. But in terms of nu 0, I think it's a little bit unclear as how they're doing it. So, okay, so, what do they say? They put a geometric distribution? Okay, all right, so good catch. So in that case, we shouldn't just have nu 0 to be a constant over here, right? So it's gonna be a prior somewhere, so let's move this up. So both of this should be related to the priors now. So let's see what we're gonna do. So nu 0, let me do sigma 0 squared. That's easier because it's gonna be a, what did they say? Gamma AB, right? Yep, so they do a gamma, so it's D gamma, I guess A and B for now. So we need like prior values for A and B over here. Okay? So I leave it here blank for now. That's something we need to fill in later. But the new, I guess, nu 0 is a geometric distribution. Okay, so I don't know about the G, okay. Now I guess it's a chance for me to demonstrate how you will figure this out. So I posted, let me bring this up. So there's a menu, a user menu that I posted on Moodle. So if you open that, you should download it and save it on a desktop, I think. But the way you can do it will be, give me a second. So the way that I would do it will be open, okay, so the menu is about 70 pages, so it's a little bit long, but you can search. So what we want the density for the geometric, right? So let's hope it has it, geometric. Okay, so they do have, okay, so they have a table over here. If you already start playing with it, and I guess they do not have a geometric. They only have hypergeometric as part of the distribution. So it might be unfortunate that we won't be able to replicate exactly what they have in the textbook. So you know what I'm talking about? Like here, the textbook is using a gamma for sigma 0 square and a geometric for, yeah, a geometric for the mu 0, but we might not be able to replicate exactly the same thing on our particular case over here. Okay, but what else? Let's just pause here. What are the distribution we can use? So here, if you read the textbook, they use a prior on mu 0 biogeometric because they want to restrict it to be 1, 2, 3, 4, like only the integer. So what are the distribution we can use? Say if now I want to use JAX to make sure that the code works. You have integer numbers over here. Or any other, any other possibilities that you want to put on? Yeah, so right now the problem is here, we are not sure how to put a prior distribution for mu 0. But the textbook, they do mu 0 to be a whole number because they said it's easy to sample from its full conditional distribution. Okay? But what's mu 0? What is it for? It's the prior for the gammas. Sorry, it's the prior for the sigma square. What does mu 0 tells us? Is it about the sample size? Because it should represent some prior belief about what we have for this sigma square, right? What do you think? We don't have to follow exactly, like obviously we won't be able to because we cannot specify a geometric over here, but what are the ones that make sense here that you would like to try? Mu 0 is the first parameter for the gamma distribution of variance, sigma square. Or in order to try, like in order to play with it, what did you try to do this part? Again, because JAX can, they don't care what you fit in. They can always figure out like a sampling scheme for you. So you can just try to enjoy the freedom of different priors that you can put. But now we're kind of stuck over here as what kind of prior we can use. And this will probably go back to previous chapters, especially the one about the normal. So I would like you to think through this now before we move on. Any idea? So the mu 0 is about prior sample size for the other gamma, like for the variance the prior for the variance, sigma squared. So just so you know, if you go back to the book, for the between example, when they did it back then, they choose mu zero to be 1 to represent their prior belief about this variance. Okay, so to show that the prior distributions are only weakly centered around the estimates. So here you can either put a distribution. So what they did, like in the book, when they talk about 8.5, it's talking about putting only whole number for this prior sample size to make it easy to sample from the full conditional. But now, like we noticed for JAX, you don't even need to worry about the full conditional because they will figure out something for you. So now you just want pretty much either you put a distribution over here or you just put a number, right? And the number is just, or the distribution should just represent your prior sample size as how much you believe about the variance. So what do you think you would do? Or what you want to do is the prior sample size. So FYI, if it's 1, it's very low sample size, prior sample size, shows very weak belief. So what do you want to put? So it's really about this two part. Yeah, so if we put 1 over here, this is saying that we're not letting it to be there is no one extra layer of the prior over there, right? So we have so Rachel is saying, you put 1 over there. So what this is doing, so let's pause a little bit of this part of the code, what we're doing. So on the top, everything stays the same, okay? But now the tricky part is how we're doing all of the prior specification. So here, the mu we know is normal, that's fine, nothing changed. And all of this are not changed either from before. But what we changed, and also this one, sorry, inverse tau as well. But what we changed is this two, the S2 square, which is the sigma 0 square. Okay? Following the textbook, they use a gamma AB. Okay, so we put a gamma AB over here. And then this mu 0 over here is the prior sample size for inverse sigma squared j. And the textbook was saying that you should try to restrict to whole numbers so it's easier to derive. But for now, we don't have to worry about that restriction. So the textbook uses a geometric distribution, but here you can use anything you want. So the way that we're doing right now is not putting a distribution on it at all. We just put a particular number to represent our prior belief. Okay, so say here we're doing 1, and here is gamma AB. So AB, I guess you can put, I don't know, different numbers. Let me just put 5 and 5 over here. But I just want to say that another thing you can do is you don't even need to specify a gamma prior for this sigma 0 square, because you can also just put it as a number as well. Okay, so there are so many different choices. Yeah. Yeah, good point. So I think, yeah, so JAX does have some picky things. So first of all, if you want to specify a distribution, you use this tilde. But I think in JAX, you cannot use equal sign to make assignment. They only take this arrow, like the arrow and then the hyphen to make assignment. Yeah, Eli?
Definitely correct me if I'm wrong here, Srini, but what I've heard, what I think maybe starting to explain is that in sigma square not, there's an arrow instead of the
Sorry, where is it?
For the like D gamma 1, it's
Oh, this one?
yeah.
Oh, sorry, it's not an error. Yeah, it should be a tilde. Yeah, right. So only if you're doing assignment, it's that arrow and then also a hyphen. But if you're doing a distribution, like, then it should be a tilde. So that was my bad. Okay. So, okay, in that case, I would like to move this up here just to keep consistent. So I have all of this to be a prior specification. And down here, it's particular. I just fixed some numbers over there. So I do over here. Okay. All right. So, I mean, I would like all of us to go back and do it later, but I just want to show you that everything else here should stay the same because this is feeding the data. But now I should also try to save one extra vector over here will be all of the inverse sigma. Okay, because now we make inverse sigma 2j. Yeah. So because now think about all of the parameters that we have. Back then we have all of the mu j, the grand mu, the particular sigma square and tau square. But now I actually should delete this sigma square because there's no sigma square anymore. Okay, but I'm saving, so let me be more consistent. So down here, I'm doing all of this. So the first two vectors, so both of this are length 100. So I have 200 parameters here with this two line, like two quotation marks. And then down here is the grand mean and the tau square. Okay. So now you're returning 202 parameters. And then of course, you should figure out, say, once you have run this, or like play with the priors a little bit here and there, you should also figure out whether, because we're using two different models for the same problem, right? One is have a fixed sigma square. I shouldn't say fixed, the one same sigma square. The other one is you have the varying sigma square based on the school. So which one is a better model for this case? And what you're gonna do? You can do posterior predictive to see if that one works than the other, or works better than the other, or other things. Yeah, sorry.
We had before it was like mu j and then it was sigma squared, which we got by assigning that like the inverse of the inverse sigma squared j. Are we?
Oh yes, thank you. Yeah, so more things to tweak over here. So this again, because sigma square is gone and inverse sigma square is gone too. So I need to change everything into this as well, right? Good catch. Okay, so in that case, I probably should not save inverse sigma j. I will post this after class, of course, but I want to show you how actually someone will actually do this. It's new to me as well. So what I'm gonna do, so Serenity points out that now, because this is a vector now, right? But we're interested in a sigma j square itself, not the inverse of it. But we put inverse because that's what JAX takes when you're trying to do the d-norm. So this is what you're gonna have. I think this line should just work. It just like work on the vector itself instead of scalar. So okay, so now you have that. But in terms of saving the parameters, because I'm curious more about the mu j's and sigma square j, so I would save them instead of the inverse sigma square that I did earlier. Yeah. No, like you mean over here? Oh, it doesn't matter. Yeah, but you should keep in mind what they are, because you will have to know which column you're like extracting. Yeah, but I did notice something. So if you tried it before, I noticed that back then, where do I have it? Sorry, give me a second. The old code that I had before, without the sigma. So Arin's question was about this thing. Okay. Yeah, so whether the order matters here. So I think ironically, I put it in this way because I think the order matters. So I put mu j and mu sigma square and tau square over here. But when I get the output, I think for some reason, this mu appears first. Because if you look at the index that I'm using in order to summarize my posterior, this mu comes first, and then it's the mu j, and then sigma square and tau square. So for some reason, that's how they store it. So I should take back what I said earlier. I guess the order doesn't matter, but you need to click, say for example, down here, I want to show you, especially about how to get the MC diagnostics for all of the mu j. Because you need to go through all of the different schools to compute the variance and the effective sample size. So over here, you notice that I'm using, so J loops from 1 to capital J, but because the whole vector, like the whole matrix over there, they stores mu J, mu first, and then all of the mu J, and then sigma square and tau square. So I have to loop from J plus 1. Yeah, but those are some subtlety, and you should all be careful about what they're doing. Again, I'm not sure why they didn't save it in the way that I asked for it, but they still save everything that we asked for. You just need to be careful. Yeah, another comment? Yeah.
I'm getting error messages that says that inverse sigma squared underscore j is not a known variable. I'm trying to figure out.
Okay, so I would say, so I will post this right after class, and we should all go back to run it. And on Wednesday when we come back, just talk about this really quick. Okay, but for today, I just want to show you how you can change the code. And I'm not 100% confident that this is gonna work. Like what Eli tried, it's gonna run into errors. So we all should go back to figure out how to make this work. And then again, I put a constant for new zero, okay? And I put a gamma prior for sigma zero square. You can try different things. You know, you might also want to just put a constant for sigma square, sigma zero square as well, instead of putting a gamma distribution. So variations of things, but I would just post the version that I have online on Moodle, and then you can use this as a starting point to play with the data. But ultimately, I would like all of us to think about whether we should have this one extra sigma j squared to be varied across schools. Because it might not make sense. You might be overfitting the data or the model because you have too many parameters, but maybe this is giving you better results. Okay, so not only just try the code itself, but also think through, now you have two different models, what you're gonna do about them in order to decide how you want to analyze your data. Okay? All right, cool. So let's go back to our lecture to talk about the new model. Okay, so the new one, so now we're entering the topic of sorry. We also use the normal as an example as how you are doing all of that, okay? And the derivation follows. So here, multivariate normal, by the name, you might guess that you're looking at multiple variables in this case. And in particular, you're assuming that they jointly follow a normal distribution. Okay, so now everything moves from a scalar to vector and matrix. Okay? But things are not that different. Derivation-wise, it's definitely more complicated, but the general idea wouldn't be that different. But I do want to talk about them first. Okay, so the example, just follow the textbook again so you can go back to read it as well. It's about the reading comprehension. It's about school students, especially just children. They're given a reading comprehension test before and after a particular instruction method. So naturally, because now even though, so you have two sets of scores, right? But they're linked because it's the same children or same child before and after. So it makes sense to model them jointly. So here we use yi1 to be the pre-instructional score for the student I, yi2 to be the post. So for each student, you're gonna have a vector of observation. Okay, so here we use the transpose over here just to make the matrix algebra easier to use later. But overall, you're looking at a vector of 2 by 1. One over here, 2 over here. Okay. So this, the whole thing is yi, okay? But you have 2 of them, and you're trying to model them together. So the reason to model them together, I think mostly is because it's from the same student. There should be some dependence between them, okay? But of course, later you can decide whether you want to use a multivariate normal for this or not. But that's gonna be after we talked about the methodology. But for now, we're not looking at scalar observation anymore. We're looking at a vector, in particular a vector of dimension 2. Okay. All right, so some questions you might be interested in asking. Do students improve in reading comprehension on average? So that will be looking at whether this gonna change, like the 2 will be larger than the 1 in some sense. And then, so that will be like asking whether it's gonna be increasing, and if so, by how much. You will be able also to compare like the absolute change in the difference. And also, can we predict? So those are the questions that people might be asking. I will show you once we set this up, how we can summarize the posterior in some way to answer those questions. But you might have other questions as well. So here, just want to emphasize at the beginning that this, you cannot claim that the method caused any changes, okay? Because this is not a causality. You're only showing whether things change between, like before and after, but you cannot say that it's because of this particular instruction method that people are improving or not. Just because I guess all of you have heard about correlation does not imply causation. So this is just a highlight and heads up over here. All right, so I posted the data on Moodle. You might download and try to look at it. And this will be the scatter plot of looking at 22 kids. So there are 22 points over here. On the x-axis is their pre-instruction score, and y-axis is the post. So if you learn, or if you have seen stuff like this, you might have some ideas of what you're going to do about this, I guess. So if anyone wants to talk about it real quick, feel free. You might learn other methods like regression, et cetera, et cetera. So you might want to do that over here. But how are you going to decide what you're going to do, or what you plot before and after? What do you think? Talk about the train. You might heard terms like correlation, et cetera, et cetera. So, anyone? What does the plot tell us? Katie?
It looks as though there's a positive relationship between the two scores.
Mm-hmm.
There are like maybe a few outliers.
Mm-hmm. So when you say positive relationship,
Looks like as one score increases,
mm-hmm.
the same student's second score.
Right. Yeah. So we do see a general positive trend. So it's over here. Train over here. In general, like for one pre-instructional score, if it's increasing, in general, the post is increasing as well. Okay. So this, and of course, there are some outliers here and there, might be. So I want you to think about what is this, like here, we talk about positive relationship. Usually in other contexts, I think when you see this, it's mostly about like 2 variables or like multiple variables, and they're trying to say like the relationship between those variables. But what does it mean here? Because each point is a specific student, right? So this positive relation over here actually gives us some backup or some justification of why we should model one student, 2 scores together. Or you should also think about for different student, even though all of the dots are different, it represents a different student. but you still have the general trend of the pre-score, or the I should say post-instructional score is positively related to the pre for one particular student. So think about the model that we're going to learn in a second. We're going to model this as a 2x1 vector, okay? And we're going to model each of the yi, so this is a vector, each of the yi as a combo together, right? So this is the big difference between what we have seen before to now. And I do want to show you that this positive relation over there does give back up, I think, in terms of whether you want to model them together. And then later you're going to see that it's going to be a normal distribution that we're going to, multivariate normal that we're going to use. So you might want to put a positive correlation for this too, because they're positively related over there. Okay? But this is part of the exploratory data analysis. It's always good to do. And okay. All right. So in this case, because we're only looking at pre and post, so you only have 2 observations for one particular student. So this will be a special case of the multivariate. It's going to be bivariate. Okay, you only have 2. So look at the notation. I mean, because this is typed up, so I use all of the bold face to be vectors and matrices. Okay, but when you write, you just need to be careful and then don't lose track of the way that you're writing it. So over here, this is a 2x1 matrix, okay? And this is gonna be, so here, this underscore 2 is 2x1, okay? And then this is the mean that is centered, this is the variance. So let's break it down a little bit. So here, so first of all, this is the notation from before. So it's going to be a 2x1 matrix, and the mean going to be 2x1 as well. Okay, so here the notation will be mu1, mu2, and transpose, but you can also write it mu1, mu2. I kind of feel like I like this way more because it's more like straightforward for me. But if you want to save space, you should use transpose over there. Okay. So for a multivariate normal, the mean vector marginally is the mean of each variable. Okay, so they jointly follow a bivariate distribution, bivariate normal in particular, but the mu1 will be the marginal mean of yi, the y1, and mu2 will be the marginal mean of y2. Okay, and the other part is the covariance matrix. So here, as you can tell, it's a matrix. It's going to be 2x2. On the diagonal will be the marginal variance of each 2. On the off diagonal, they're the same, symmetric, is the covariance of this 2. Okay, so here, this is what I wrote, like what I just said is in the words over here. And lastly, the correlation, you will be able to get it from the covariance divided by the square root of the product of the variance. Okay, that's definition. Okay, and down here, I give you 3 different plots. This is when covariance is 0, this case, just randomly scatter around. The left one is correlation, correlation negative 0.5 and positive 0.5. Okay. All right. So let me bring up a whiteboard. Just notation wise, in the past, this is univariate. Bivariate. So this is like the particular way that I think more intuitive. I'll just share with you over here. Let me use because for me, this will always help me keep track of the dimension. Okay? But both of this means the same thing. So here, once you do bivariate, you'll be the first observation, second observation, bivariate normal. So over here, I should have a 2 as well. Okay? So this will be the mean vector. So like I said before, marginally, that's what mu1 and mu2 are. Okay? And the covariance matrix, the diagonal will just be the variance. Okay, so sigma 1 square is variance of y1, and sigma 2 square is variance of y2. Okay? And lastly, the off diagonal is 1, 2, 2, 1, but it's the same number because it tells you the covariance between these two. Okay, so you can write this way. Okay, so these are all of the notations. All right, so, and naturally, if you bring this to multivariate, you're just gonna have a p over here. This is gonna be a p by 1 vector, and this is gonna be p by p, okay? And diagonal, it still tells you all of the marginal variance, and the off diagonal would be much more complicated because you have many more terms, but just think in terms of the matrix, that's gonna tell you each position, gonna tell you which covariance that represents for. Okay? And also here, of course, gonna be p by 1. Okay? But we're gonna focus with the bivariate because it's easier to deal with, and also that's what the particular data set we could use. All right, so some matrix review over here. And I also printed out for you as well. I posted, but you can also, printed out for some useful matrix algebra. Can you pass it around? Thank you. So that's mostly for the derivation if you're curious about how things are derived. And that's, again, not required, but I think it would still be nice to go through some of the general idea. All right, so if it's gonna be, over here. Okay. So this is the general form of multivariate, okay? So if it's p dimension, mu will be p by 1. Sigma is the covariance, gonna be p by p. Diagonal elements to the variance and off diagonals equal to the covariances. So this is the general form with different j and k. Okay, so j is between 1 and p. K, thank you, between 1 and p as well. Okay. And in particular, the covariance matrix needs to be positive definite because otherwise you cannot be a proper covariance matrix. All right, so the PDF. Okay, so the PDF is a multivariate normal. You can think of it as an extension of the univariate, but I do want to show you what the form is. So here it's a p dimension. So just bear with me. You have, so this is, look, it's not a proportional. So this is the entire PDF, integrates to 1. Okay, so you have the pi part. Okay, so it's 2 pi to the power of negative p over 2. The sigma, it's the absolute value. Sorry, I shouldn't say. It's not an absolute value. It's the, what's the name for this? Yes, thank you. The determinant to the power of 1 over negative 1 over 2. Thank you. And then in the exponent, it's going to be in the matrix form. Okay, so I will pause here for a little bit, and I will write the regular univariate case over here, so you can have a look at how it is extended. So this is the univariate normal. The multivariate normal, so you see that this 2 pi to the power of negative p over 2 is similar to extension over here. Okay, this is univariate, but now you have p dimensions, so raised to the power of p negative p over 2 instead of raised to the power of negative 1 over 2. And the variance over here, because over here it's gonna just be a sigma, 1 over sigma. So this is the determinant, that's the part. And then in the exponent, I just want to show you that it's not that complicated from before. Before, because it's univariate, so you divide it. So this 2 over here is 1 over 2, that's the same. But now, because you're dealing with multivariate case, the scalar is divided by sigma squared, but down here, it will just be the inverse of that matrix. But it should be multiplied in between just to get the dimension works. Okay, so this will be, what's the dimension for this? So y is p by 1. Mu is p by 1 as well. So this will be 1 by p, right? Once you do the transpose. The inverse of this is p by p. And this is p by 1. So once you do this, that becomes a scalar. Okay? Yeah. So yeah, it's definitely much more complicated to compute, but just want to show you whole thing will be a scalar as well. Okay? And you can also do precision matrix. Okay, so precision matrix, everything just replace a sigma inverse to be phi. Okay, and one last useful result over here is if it's going to be a multivariate normal. So if you know this is what we know before. You know that if you multiply a constant in front of the random variable, it's still going to be a normal, but it's going to be, sorry, it's going to be normal scalar. It's going to be a mu and a squared sigma squared. Okay? But now everything is in terms of matrix. So if you multiply a vector in front of it, it's going to be a mu, and this is a sigma a transpose. Okay. So that's the square part. Yeah. So because it's matrix now and vector in this case, you cannot just do square. The multivariate normal theory, you need to do a sigma and then a transpose. Okay. So all of this is written on this handout, so you can keep that in mind. All right. So that's just the dimension, like the PDF. And for the remaining 7 minutes, I will talk about the semi-conjugate prior. And we're going to introduce a new distribution here, which might take more time to do it. So maybe I will pick that up from Wednesday. But I want to set it up the general framework over here. So our sampling model, the data follows a multivariate normal, right? And what's the unknown here? Just look at this part. The parameters. You have a mu, which is p by 1, which is a vector. And you have a p by p matrix, which is the covariance matrix. Okay? So naturally, if you want to do Bayesian inference, you should put priors for both of these two. Okay? So just a little bit review. Back then, when we do this, the semi-conjugate prior that we did before is mu. So this is the data model. And this is the prior. So what we did before for the semi-conjugate, we have a normal, mu 0, sigma 0 square. And then for sigma square, we put an inverse gamma. Let me just do AB over here to simplify. Okay? So this was the semi-conjugate prior that we did. Okay? And the semi-conjugate, conjugate. The semi-conjugate, if you still remember, the semi-conjugate case is you cannot derive the posterior, but you have full conditionals. So we did a Gibbs sampler back then to make this work. Okay. The conjugate one that we did is this going to be given sigma squared. Remember, it's conditioning on the variance, and then you derive a not full conditional. You derive the posterior. So we didn't even need to use a Gibbs sampler to make it work. okay? But the semi-conjugate case is to have independent priors, and you use Gibbs. Okay, so this is what we did before. So for the multivariate normal case, you will guess it's not that different. What we're gonna do is for mu, you're gonna have a semi-conjugate prior gonna be a p-dimension multivariate normal. Okay, and we use mu0 and gamma 0 to be the mean vector and the variance covariance matrix. Dimension is the same. So the new distribution that I said we're going to introduce is this called Vassar distribution. We're actually going to put that into the precision. Okay? And just so you know, we're going to get into the detail. But remember, for the precision, which is that phi that we did before, what did we put it on? We put a gamma, right? Back then. We put a gamma for the precision matrix. So the inverse, sorry, the Vassar distribution, it's a multi-dimension generalization of the gamma distribution. Okay? So this is the biggest takeaway, okay? I mean, it's not a straightforward process to understand the motivation of Vassar, I think, but at least you should know that it's just a multivariate generalization of the gamma distribution to the higher dimension. Okay, so if you do this semi-conjugate prior, you're guaranteed to get a Gibbs sampler to work because you can derive the full conditionals and you can code it up your Gibbs sampler in that way. Okay, but as you can tell, I mean, deriving the full conditional might not be that trivial in this case. Okay, everything now works in matrix. So the particular hint that I put on over here, like the useful results, one thing you notice is about the trace. Okay, so trace of a matrix is and trace is only defined by square matrix. Okay, and trace of a matrix is the sum of the elements on the main diagonal. So there are some properties about the traces. So that's the first part of this handout. And the second part of the handout, as you might guess, is I remember back then when we were doing the univariate case, we showed some trick to like expand the square term and then try to collect some terms together, some other terms put it aside, and then put it into proportional. All of that was trying to help you to recognize the full conditional or like the posterior if it exists. Okay, so here we're doing the same thing, but everything is in multi-dimension. So down here, especially the first bullet point of the second part over here, is give you a hint that if you see a density of the random vector x in dimension p to be proportional to something in the exponent in that case, in that particular form, you can actually recognize that it's a multivariate normal. Okay, so that's just something I think you need to convince yourself that is true. And then once you know that, deriving the full conditional is not that hard. Okay, so try not to overburden yourself with all of this information. I think the biggest takeaway is everything now works in terms of matrix and vector. And then the tricks that we will do, or you're supposed to know how to do, will be pretty much all listed on this page. And I think is exercise here and there to make sure that you can get them right. Okay. All right, so the Vassar, I think I would just like talk about this in particular on Wednesday. I think it's a little bit too much information at the moment over here. But I do want to maybe just show you the full conditional so you know that I'm not lying. You can get the full conditionals, and it's kind of in this weird shape. It's very convoluted, I agree. But the general idea, if you look at it, yeah, let's just spend the one last minute over here about this. This is the full conditional of the mean, okay? Look at what it is. It is complicated, but if you look at this, it's gonna be P by P over here, right? Because it's the covariance matrix for that P by 1 thing. So it's gonna be, so this is from the prior, okay? And this is also from the, no, this is from the prior, this is from the data, okay? So this again is a combined precision. Everything works in matrix now, but it's still combined because the dimension is the same, okay? So this is P by P, and you take the inverse to get the variance right, to get the precision right. And here, you see, this is the precision itself, okay? And multiply by the weighted average from the data and the prior. Okay? Definitely much more complicated, I agree, but similar idea from before. Okay? And we showed over here, I said it's a p-dimension gamma distribution. So the first parameter is the sum of the sample size and then the prior size, like what we have seen before. And here is more complicated, but this is from the prior and this is from the sum of square from the data. Okay, so again, the derivation is not required, but I do want to show you that it's not way more complicated before. Some of you might feel more comfortable to do the derivation and convince yourself this is true. But if you don't feel like it, you should at least understand that this is the gist from all of the supposedly you should do derivation. Okay, so on Wednesday when we come back, I will talk about the Vassar distribution and then demonstrate this particular exercise. But I do want you to try it before class as well. So I will send an email. One thing is about the JAX code for the more complicated JAX model that we just did. I would like everybody to try and then run it and come up with some ideas. And then the other one is, yeah, no, that's the only one. Let's just do that for Wednesday. Cool. All right, cool. And the homework is due next week, so you should have enough time.